Well, hello everyone. Chapter number 3, integrals, part 1, day number 1. Did your parents ever tell you that they wanted you to master a task so well that you knew it forward and backward? Well, my dad used to say that all the time, as well as make terrible dad jokes, but that's beside the point. Why do I say that? Well, because differentiation is learning a process forward, and integration is executing that same process except backward. So we're about to make the old adage, learning it forward and backward, come true. So let's look at our topics for today's lesson in day number 1, antiderivatives and indefinite integrals. Fundamental theorem of calculus, part 1, along with definite integrals, fundamental theorem of calculus, part 2, and then average value. First thing I want to highlight here is an indefinite integral as opposed to a definite integral. So an integral has this symbol. This is the integral symbol. We would take the integral of a function f of x with respect to a variable. This is an indefinite integral. And a definite integral has almost the exact same form, but what makes it a definite integral is it goes from one limit, for example, from 1 to, say, 5. So these limits right here make this a definite integral, as opposed to an indefinite, which has no limits. Okay, let's get it started. All right, so what is an antiderivative? Well, an antiderivative, big F of x, is such that big F prime is equal to f of x, or the integral of f of x with respect to x is equal to big F of x plus c, where c is called the constant of integration. Okay, so an antiderivative is simply the opposite of a derivative. Makes sense? So let's do a few examples. Find the antiderivative, which is big F of x, for each function f of x. So if I were to take the derivative of big F of x, I would get sine of x. All right, so the derivative of big F of x is sine of x. Well, clearly I know that big F of x, just from memory and experience, would be negative cosine of x. So big F of x is negative cosine of x. So is the derivative of negative cosine of x equal to positive sine of x? Yes. Therefore, the antiderivative or integral of sine of x with respect to x would equal negative cosine of x plus some constant c. Okay, now I do kind of want to talk through a little bit of why this constant of integration shows up. So let's take, for example, the integral of x dx. Well, what would the integral of x dx be? Well, that would be x squared over 2. And we tag on this plus c. Let's see why. All right, so the integral of x is x squared over 2. Well, what would x squared over 2 plus 0 look like? Well, it would look kind of like this. How about x squared over 2 plus 1? It would look kind of like that. X squared over 2 minus 3. Well, it would kind of look like that. Now look at the slopes for each of those functions at 0. They're all 0. How about the slopes for each of the functions at this x value, whatever that might be? They're all the same. So because the slopes are all the same at the same x value, that means that the integral of x dx gives us a family of possible functions, right? And c just helps us to distinguish between each of the members of that family, right? As we can see over here. Okay, so let's do number 2. What is the integral of 1 over x dx? Well, that would be the natural log of x plus c. If I took big F, which is the natural log of x plus c, and I took its derivative, I should get f of x. What happens is I get 1 over x for the derivative of ln of x, and then c drops off. So you can see that big F, its derivative, turns into 1 over x. Okay, most of these are just from memory. So the integral of secant x tangent x dx is the function whose derivative is secant tangent, which is secant x plus c. Okay, the next couple I've tried to throw somewhat of a tricky setup. F of x in number 4, the integral of 2 over 3 x to the 1/3 power dx is equal to x to the 2/3 power plus c. And you can always differentiate that right side in order to determine whether or not your quote-unquote guess is correct. So if I differentiated x to the 2/3 power, I'd get 2/3 x to the negative 1/3 power, and the c would drop off. So I would have my correct value for little f of x. Okay, the integral of 1 over 1 plus x squared by memory we know is arctangent of x. Don't forget c. And then for number 6, the integral of k x to the 4th dx will be k x to the 5th over 5 plus c. Taking the derivative of that, I'd see that I did that accurately. Okay, those are a few antiderivatives. Don't forget the constant of integration, which is used when you have a definite integral. Let's go on to the next slide. Okay, the fundamental theorem of calculus part 1. A lot of math words here. I'm going to make it as simple as possible. If y equals f of x is a function that is continuous on this closed interval a to b, where a is less than b, then the shaded region A represents the area between f of x and the x-axis for for x between a and b. The fundamental theorem states, now I'm not doing a proof of this, however, if you want something along those lines for a little bit more concrete proof as to why this works, talk to me on the side, we'll work it out. Okay, the integral from a to b, notice this is now a definite integral of f of x, or the area under the curve, is equal to big F at b minus big F at a. Okay, now the notation that you see or will see on my keys is that the integral from a to b will be big F of x evaluated from a to b, and that is equal to big F at b minus big F at a, where the derivative of big F is little f. So let's look at a couple of examples here utilizing fundamental theorem part 1. Okay, so what would the integral from 0 to pi of sine x equal? Well, we already spoke to this, but we said that the integral of sine x dx is negative cosine of x. Now, with a definite integral, we don't add that constant of integration. We just evaluate from 0 to pi. So that would be negative cosine of pi minus a negative cosine, notice how I changed the sign, of 0. So evaluating that further, negative cosine of pi, well, cosine of pi is negative 1, so negative 1 is 1, plus cosine at 0, which is 1. So the area under the curve for sine from 0 to pi, so from 0 to pi of sine of x, that area right here, that shaded region, has an area of 2. That's pretty awesome. So graphically you could see that's pretty cool. All right, let's look at number 2. So the integral of e to the x, that's awesome. Love e to the x. It's going to be e to the x evaluated from 1 to 5. So that'll be e to the 5th minus e. Therefore, I can't really do much with that. I guess I could pull out an e that's really not doing a lot to help me. But it is what it is. I would say either this form or this form would be acceptable. It depends on what you're prompted in the context of your question. Okay, so from 1 to 5, well, I know that this point is 0, 1. I know that this point right here would be 1e. Therefore, I'm going from 1e to 5e to the 5th. So this area right here would be e to the 5th minus e. Okay. I'm not going to go through the calculator work to figure out what that is to 3 sig figs. You could do that on your own. Okay, so now what about this? I don't know the integral of the absolute value of x. So really, what am I doing here? I'm finding an area between the x-axis and the absolute value. And it's going from -1 out to 5. So what does the absolute value look like? Well, it's this V shape, right? Where this would be 5 and this would be 1. Okay, so I'm really finding geometrically the area of 2 separate triangles. All right, so let's do that. So the integral from -1 to 5 of the absolute value of x with respect to x is equal to the area of a triangle with a base of 1 and a height of 1 plus the area of a triangle with a base of 5 and a height of 5. So this area would be the equivalent to 1/2 plus 25 halves, which looks like it comes out to be 13. So the integral from -1 to 5 of the absolute value of x dx is equal to 13. All right, again, if you're interested in what the actual integral of the absolute value of x is, we can talk on this side. All right, let's look at the next slide. All right, let's continue with a little bit more work involving the fundamental theorem part 1. Assuming that f is integrable on the interval from -4 to 3, evaluate each of the definite integrals. Okay, so the area from, in part A, the area from -4 to +3. Okay, that's going to be all of those areas combined. Now, what I'm going to do first is I'm going to find the area of this green region. Okay, it's going to be interesting region. That area, as we work from left to right, if the area is above the x-axis, this area will be positive. Okay, then I'm going to look at the red region, which looks like it's a half circle. I don't think that I prompted us with that obviously here, but the problem originally did. This area will be a negative region since the integral is headed from left to right. If the function is below the x-axis, we consider it a negative area. Unless, of course, you look at part C, we're going to take the absolute value of each of the areas and add them up. Okay, so let's find the area from -4 to a -1, which would be the green region of f of x with respect to x. Okay, so that would be a trapezoid in this first space and a triangle in the second space. So the trapezoid would be 1/2 the sum of the two bases. The first base would be a height of 1. The second base would be this dotted line right here, which is a height of 3. And the height is the distance between these two bases, which is 2. All right, so then I'm going to add the triangle, which has a base of 1 and a height of 3. So it looks like this area, this green space, will be half of 8, which is 4, plus half of 3, which is 1.5. So this space will be 5.5 units. Okay, so I'm going to kind of gather that over here, and then I'm going to find the area here in this third space. Well, that's half of a circle with a radius of 1. So that's half the integral, the integral from -1 to 1 of f of x is equal to half of pi times 1 squared. So that's going to equal pi over 2. All right, so I've got plus, now be careful, this is not pi over 2, this is minus pi over 2. Negative, since it's below the x-axis. Okay, and then the triangle in blue, we'll call this area 4, will be the integral from 1 to 3 of f of x with respect to x. That'll be 1/2 the base, which is 2, times the height, which is 1. Now I know that the height is a -1, right? This is a length of -1. You could either use that as a -1, or you can just understand that the area beneath will be negative. Okay, so I'm going to get an area of 1 for that space. Excuse me, -1. Almost did it to myself. And -pi/2. So it looks like this area from -4 to 3 is going to be 4.5 minus pi/2. Okay, now let's say that I take and I flip the limits of the integral, right? I flip the -4 and the 3. Well, if I flip the limits of the integral, that's the same as the opposite value of the integral with its limits the opposite direction. Therefore, the integral from 3 to -4 is going to be the opposite as it was from -4 to 3. And there you go. You got it. Now, interestingly enough, you can consider part C, just taking the absolute value of each of the areas. Okay, or you could consider that as flipping those spaces, right, geometrically above the x-axis. So if I added all those values up, I would get 5.5 plus pi/2 plus 1, which would give me 6.5 plus pi/2. All right, a little bit more there, obviously, with the fundamental theorem part 1. Okay, let's look at some rules or properties of integrals that you might find useful. We've got the the sum and difference rule. If you got two functions, split them up, take the integral separately. A constant multiple. If you got a constant times a function, pull that constant out. Sometimes that can be beneficial. It makes it easier to see the antiderivative. Reverse interval, okay, like we just did in part B up there in the previous problem. If I go from a to b of f of x, that's the same as the opposite sign from b to a of f of x. Just change the sign. Zero length interval, it seems kind of dumb, but if you take the integral from a to a of f of x, the area under that curve is going to be 0. And it comes up relatively often. Okay, adding intervals from a to b plus b to c is the same as the integral from a to c. Okay, let's keep moving. Okay, fundamental theorem of calculus part 2. We're going to develop this part. Okay, so let's let f of x actually equal an integral. Okay, let me explain a couple of things here. First of all, f of x, g of x, and h of t are all functions. A is a constant, some value, doesn't matter. Okay, so f of x is considered the function which accumulates area from a to g of x. Kind of weird to think about. I'm going to make it really, really simple. Okay, now t, why is there a t here? Well, because we can't have an x here for this function on the inner part because x is already represented here and this is our independent variable here. So we have to have, this is called a dummy variable. You'll see that in every fundamental theorem part 2, but it might be, a different variable other than t. Okay, so don't worry about it. It's nothing that's gonna stump you. You don't need to worry about it at all. Okay, so let's find f prime of x. So first what I'm going to do is I'm going to integrate using the first part of the fundamental theorem. So I'm going to use FTC part 1. So what would be the integral of h of t dt according to the first part of the fundamental theorem? Well, it would be big H. Let's assume that we've got limits, right, like we do. It'd be big H of g of x minus big H of a, right? So by the first part of the fundamental theorem, that's what we should get. So I'm going to integrate. That'll be big H of t, and I'm going to use a different notation here, from a to g of x. All right, so what is f of x? F of x is big H of g of x minus big H of a. Right? No constant of integration because it was a definite integral. All right, so let's keep it simple. Let's take the derivative. We're trying to find f prime of x. Let's do it. Okay, so that would be big H prime of g of x times, using the chain rule, g prime of x minus, what happens if I take the derivative of a constant? Well, that drops off. Okay, what if this wasn't a constant? Well, then you would take the derivative of h of that function and then multiply by the derivative of the inner function using the chain rule. Now, one thing that I want to get rid of here is I want to get rid of big H prime. I don't like that notation. I don't see it in the original expression. So by definition, big H prime is equal to H. Right? We talked about that earlier with the first part of the fundamental theorem. So there you have it. F prime of x is h of g of x times g prime of x. Now a couple things, and we'll look at a couple of examples here in a minute. But a couple things that you need to be aware of. If you have a limit, okay, if you have a limit of a constant and a function, you always want to have your function on the top. Okay, so whatever you got to do to manipulate it, get your function on the top. It'll make life a little bit easier. Okay, if you have two functions, that's fine. All you're going to do is you're going to take and you're going to input g of x into h of x, and then multiply by g prime of x minus, and then you'd input this function into h of x and multiply by the derivative of that function. You'll see in a couple of examples here coming up. Okay, let's keep scrolling down here. As you can see, using the fundamental theorem part 2, f prime of x equals h of g of x times g prime of x. It always works. All right, let's look at some examples. All right, so for example, let's find f prime of x for number 1. Let's take a look at the form that we have for fundamental theorem part 2. F of x is equal to the integral from some constant to g of x. In this case, g of x is x of h of t with respect to t. H of t equals cosine of t. Therefore, f prime of x is going to be h of g of x times the derivative of g of x. So it looks like the derivative is cosine of x. Okay, let's continue on and look at number 2. All right, so we've got a little bit more to do here. The derivative in the last one of g of x was simply 1. The derivative here for g of x is not going to be 1. So f prime of x will equal h of g of x times the derivative of g of x. Therefore, I would rewrite f prime of x as 2x e to the x squared. At this point, you might be asking, like, why? Why are we doing this? Well, I wouldn't necessarily worry about it. We're going to see the applications of it later on. But for now, just get used to the mechanics. Okay, check it out now. I've got a g of x here, and I've also got a function here. I'm going to call it q of x. So if I have a function, let's say the integral from q of x to g of x of h of t dt, what would that look like if I took its derivative? Well, that would be h of g of x times g prime of x minus h of q of x times q prime of x. Okay, so let's work that out for this one here. So f prime of x will be 1 over x squared squared plus 3 times the derivative of x squared, which is 2x. Okay, so that's h of g of x times g prime of x. We'll clean that up in just a minute. And then we're going to subtract h of q of x times q prime of x, which is 1. Right? The derivative of x is 1. Therefore, f prime is equal to 2x over x to the 4th plus 3 minus 1 over x squared plus 3. There you have it. That's f prime for number 3. Let's keep moving on to the next example. All right, average value. This is a very interesting topic, and it's related to what we're doing here. So let's talk about it. The average value of a function f of x, which is considered f of c, I'll show you what that looks like graphically, on an interval from a to b, where c is between a and b, can be found using the following formula. So what the heck does this mean? Okay, so one of my friends back in the day considered this like the water tank problem. So here you go. There's a big pool of water, right? So the water has waves in it. Something happened. Somebody jumped in. I don't know. Whatever. Okay, so the integral from a to b of f of x dx is the area under that curve, right? I think we can all agree to that. Now, if I were to consider the average height of the waves, though, I would say probably right in here, right? This would maybe be the average height of the waves. Okay. Looks like that's splitting the difference pretty good. So if the water settled, right, this would be f of c. Well, it looks like the average value occurs in a couple different places. Right, there's C1, C2, C3, C4. So how do you get that average value? Well, you take the area and you divide it by the length of the interval, and that's at the average value. Cool. All right, so let's apply this to an example. Let's look down here. The temperature T in degrees Fahrenheit of a glass of lemonade T hours after being placed in a room with a constant temperature of 70 is given by T of T, as you can see there. The initial temperature of the lemonade is 40 degrees Fahrenheit. Determine the average temperature of the lemonade over the first 3 hours. So clearly the lemonade is warming up, right? It starts at 40 degrees, the room temperature is 70, so it's going to warm up to that room temperature and hit some kind of horizontal asymptote there. Okay, so let's determine the average temperature. How would we do that? Well, based on our formula for average value, I would take 1 over the interval of time, which is hour 3 minus hour 0, of the integral from 0 to 3 of t dt. Lots of t's going on there. This is going to be our average temperature on that interval. Okay, now clearly we would need a calculator for this. Actually, let's see if we can dig through it. That would be 1/3 the integral from 0 to 3 of 70 minus 30 e to the negative 0.5 t dt. Nope, I'm using a calculator, okay? So go ahead and plug your function t of t into your calculator as y1, okay? Okay, a couple things. Your calculator will likely, unless you're to mess with the modes, just ask you or prompt you with x as your independent variable. Totally fine, not a problem. Okay, so now that you've got that plugged in for y1, I want you to hit the math button and then 9. That will bring up an integral with some space here. Okay, at least on my calculator, it looks kind of like this. All right, so what do I want to fill these in with? Fill this in with a 0 and a 3 and plug in a y1 here. And the way you can get a y1 in there real quick is press alpha, which is the green button, and then trace, and then press the number 1, and that'll pull up y1. And then, of course, plug an x in here. All right, so I'm doing the same right now, 0 to 3, alpha trace y1 in terms of x. Boom, I got an answer. Okay, so here's the number 1 mistake. Okay, you get an answer and you say, ooh, great, I got 163.388. That's the average temperature of the lemonade. Holy cow, that would burn. All right, you forgot the 1/3 out in front. Divide it by 3. And your average temperature ends up being 54.463 degrees Fahrenheit, which in the context of the problem makes a whole lot more sense. All right, now, just like I did, I found those 4 C values where the water or the time or whatever distance from the edge of the tank equaled the average value. I want to find the same thing here. So what do? At what time was the lemonade this temperature? Well, I've got y1, I got t of t plugged in there. Now in y2, I want to plug in that value, 54.463. Now, instead of putting in the rounded value, what I'm going to do is I'm going to press stow. Okay, so press stow, and then alpha. Okay, alpha, and then I'm going to put this value in as whatever letter I want, right? So I'll just put it in as A. Enter. Now I'm going to go back to y1, or excuse me, to y equals, and in y2, I'm going to recall alpha A. Oops, I didn't want to do that. I just put it in y1. I'm going to recall alpha A. And I'm putting in for y2 alpha A, right? I press alpha and A and it puts it right in there. Now, what am I going to do on this interval from 0 to 3? So I'm going to go to my window. I'm going to change my x minimum to 0, x max to 3, y min to 0, y max. I'm going to go up to, let's go to 50. Let's go to 60 so I can see it. Okay, now what that's going to do is it's going to create a window here. So I'm going to go from 0 to 3, and 0, clearly not to scale, to 60. I don't know what the functions are going to look like. So it looks like here I've got like my temperature, T of T. So that's Y1. And then I've got this horizontal line, which is Y2, right? Y2, which equals, about 55 degrees or whatever it is, 54.463. So I'm going to figure out where those intersect. And the x value where those intersect is the time when the lemonade hit its average temperature. Let's find out. So I'm going to do second trace. Okay, second trace. Let's put these over here. Press the second button, then trace. Okay, then I want to go down to option 5. Just press the number 5. It'll take you right to intersect. And then you're going to have a little cursor. Right? You're going to have a little cursor, and it's going to show up on one of the functions. I don't care where it is, right? Just press enter. Then it'll say second curve, and it shows up on the other function. Enter. And then press enter again. It says guess, I don't care. Press enter again, and it'll find you that point of intersection. And that point of intersection ends up equaling, in this case, t equals 1.316 hours. So 1.316 hours into the 3-hour interval, our temperature hits the average temperature for that interval. All right, guys, that's it for day number 1 of integrals. Shoot me a message if you got questions. Otherwise, we'll see you next time.